Hello all, this is section 1.3 video 2, linear combinations and span. So if you watched the last video and wanted to know what does any of this have to do with linear systems or matrices, yeah, I'll answer that question in a sec. Before then, let's talk about linear combination. So given vectors, v1, v2 through, or yeah, all the way up to vm in Rn, we say that the vector y is a linear combination of these vectors v1 through vm if we can find scalars c1, c2 through cm with the property that y is the sum of c1 times v1 plus c2 times v2 plus all the way up to cm times vm. So let's give a couple of examples here. So I claim that 5.1, the vector 5.1 root 2 is a linear combination of 1, 0, and 0, 1, and R2. And if that's true, I should be able to tell you what these scalars are. And so what? It looks like it should be 5.1 times 1, 0 plus root 2 times 0.1. Okay. And this is a example that does not communicate most of the challenge in actually doing this because I picked easy vectors to make this work, but hopefully it illustrates a little bit what it means for some vector to be a linear combination of two other vectors. So let's try a more challenging question. So we've got B is some vector 0, negative 1, 5. We want to know, is B a linear combination of the vector 1, 2, 3 and the vector negative 2, 4, 2? So we want to know, can we find scalars, real numbers, x1 and x2, so that x1 times a1 plus x2 times a2 is equal to this vector B. Okay, and so let's break down again what it is that we're asking. So we really want to know, can we solve what x1 times the vector 1, 2, 3, that was what a1 is equal to, plus x2 negative 2, 4, 2 is equal to b, which was 0, negative 1, 5. And let's keep on trying to make this look more and more similar to something we've seen before. So we know how to do scalar multiplication. So we can just multiply these scalars inside. And we'll get x1, 2x1, 3x1 as one vector, and the other vector is going to be now negative 2x2, 4x2, 2x2. B hasn't changed at all yet. We know how to add vectors, so we may as well add these two together. We end up getting what? x1 minus 2x2 minus 2x1 plus 4x2, 3x1 plus 2x2 is equal to 0, negative 1, 5. But we also know if two vectors are equal, that means the first entries are equal, and the second entries are equal, and the third entries are equal. So really what we get is a linear system. Look, we're going to get that x1 minus 2x2 is 0, 2x1 plus 4x2 is negative 1, and 3x1 plus 2x2 is equal to 5. I guess we haven't been using this brace here, but it's a linear system. So these vector equations, like this, are equivalent to linear systems. Okay, so what we know then is that, well, okay, B is going to be in this, where are we? B is going to be a linear combination of A1 and A2 if this linear system has a solution. So B is a linear combination. I'm going to say linear combo now and forever because combination is a long thing to write out and to say. So B is a linear combo of V1 and V2, provided this linear system has a solution. Has a solution. Okay, we just spent like a million videos talking about how to solve linear systems. So let's do just that. If this is a linear system, we can pull out the augmented matrix really quick now because we're all pros. This is 1, -2, 0, 2, 4, -1, 3, 2, 5. So let's do what we always do, take the second row and change it to row 2 minus 2 row 1. Take our third row, subtract 3 times row 1. We'll get back 1, -2. Oops. What's going on here? -2, 0, 0, 8, -1, 0, 8, 5. All right, and we can do this once more by doing what are row 3 minus row 2. 1, -2, 0, 0, 8, -1, 0, 0, 6. Ah, okay. And this is as far as we need to go. Oops. This is as far as we need to go because we saw last time, the equation in our linear system that this corresponds to is that 0 is equal to 6, which can't possibly be true, which means there's no solution to our linear system, which means there are no scalars x1 and x2 that make B a linear combination of a1 and a2. Oh, I'm sorry. Our vectors are a's, not b's this time. A1, A2. Okay, so no solution by theorem 2. So this means B is not a linear combination. Linear combo of A1 and A2. Okay. And we can quickly summarize sort of what happens in general. This was a case of like vectors in R3. More generally, what happens if you're given a vector equation like x1 a1 plus x2 a2 plus all the way up to xn an is equal to b. This vector equation has exactly the same solutions as the linear system whose augmented matrix is, the matrix that looks like this. A1, A2, up to AN, B. So here we're imagining some big long matrix where the first row, first column is A1, the second column is A2, the second to last column is AN, and the augmented column is B. Right, that's what we did up here. This is our A1, this is our A2, this is our B. So in general, anytime you've got a vector equation, it boils down to the solutions to the linear system corresponding to that augmented matrix. And in particular, B is a linear combination of the vectors A1, A2, all the way to AM. Do I want M here? Maybe it's not important right now, but let's be consistent. I think I want M. Okay. B is a linear combination of the vectors A1 all the way up to AM exactly when there's a solution to the linear system corresponding to this matrix. Okay. So then closely related to the notion of linear combination is the notion of span. And so if we're given some collection of vectors v1, v2, up to vp in Rn, the set of all linear combinations of these things is called the denoted span of v1, v2, all the way up to vp. And called the subset of Rn spanned or generated by these vectors. Okay, so the span is the collection of all vectors of the form scalar times one of the vectors that we have, plus scalar times vector plus scalar times vector. Okay, so yeah, another quick example. The zero vector is in every span. We can just grab each of our constants to be zero, and that'll produce back the zero vector. So we could take C1 equal to C2 equal all the way up to CP, have them all be equal to the scalar zero. That will produce, that produces the zero vector in the span. Okay. So let's look at a more challenging example. If we've got V1 is 1, 0, 0, V2 is 1, 1, 0, and B is 3, 4, 1, again, we might ask, is B in the span of these two vectors? Or in other words, is B a linear combination of these two vectors? Yeah, so is B a linear combination of V1 and V2? In other words, yeah, are there real numbers x1, x2? So that what? So that x1 v1 plus x2 v2 is equal to b. Okay, and based off of the summary that we just saw, all we need to do is create the matrix whose first column is v1, whose second column is v2, whose third column is b, and see if it's consistent or inconsistent, or see if it represents a linear system that's consistent or inconsistent. So by our summary above, yeah, we just need to check if the linear system associated to this matrix, which is 1, 0, 0, 1, 1, 0, 3, 4, 1, is consistent or inconsistent. Inconsistent. But okay, this is not so hard either, right? We know exactly what theorem 2 says. It tells us exactly when a linear system is consistent or inconsistent. And here we've got exactly what we don't want to be consistent. We've got rows of all zeros except for that last entry, which is non-zero. So again, by theorem 2, this system is inconsistent. So B is not a linear combination of V1 and V2. And actually, we could have realized this by staring at it really hard. Look, there was no constants in front of C1 and C2 are going to produce anything but 0 in that third entry. So there's no way we're going to produce 1 somehow. It just wasn't going to happen. Yeah. Okay. So maybe we might reasonably ask, okay, well, if we change B and make it 3, 4, 0, then does it work? So let's ask that. Figure this out. If B is now 3, 4, 0, is it true? Is it true that B is in the span of V1 and V2? Yeah, so let's check. Okay, so again, the associated matrix that we should look at is still made it of V1, V2, and the new version of B, 3, 4, 0. Okay, and our theorem 2 says no problem with a row of zeros hanging out. We still should just look for whether or not there are any free variables. And so it looks like not, right? We can just do our row 2 minus row 1 and get back 1, 0. I'm sorry. What do I want? What do I actually want here? We actually want row 1 minus row 2. To get 1, 0, negative 1, 0, 1, 4, 0, 0, 0. So this is telling us x1 is negative 1 and x2 is 4. Okay, so certainly we have a solution. So B is a linear combination, and this is even telling us what values of x we should use to make B a linear combination of v1 and v2. So let's check that's true. So check. Yeah, so our claim is now that B is actually equal to negative 1 v1 plus 4 v2. So let's check. Negative 1 v1 plus 4 v2 is negative 1 times the vector 1, 0, 0 plus 4 times the vector 1, 1, 1, 1, 1, 0. Which is what? Negative 1, 0, 0 plus 4, 4, 0. Okay, negative 1 plus 4 is 3, 0 plus 4 is 4. Yeah, okay, that checks out. That is equal to our vector B. Okay, and that is the end of our second video. I'll see you all in a sec for our third and final video for section 1.3.